The first thing you need to know about chemical equilibrium is what we mean by an open and a closed system. So, for an open system, it means particles can get in and out and energy can get in and out. So, if you look at this first diagram, you can see matter can go in and out and energy can go in and out. So, this is a totally open system. A closed system is one where energy can still get in and out, but the particles cannot. So the particles are trapped. So this could either be because they're in the solid and the liquid phase and no gas is formed, or there are some gases formed, and then you must just make sure that you put a lid on it. So don't think that a closed system has always got a lid on. We'll put a lid on it if there are gases formed, so the gas can't escape. So a closed system, matter stays inside. And this is the one that's important for this chapter. We're going to work in a closed system. An isolated system would mean that you've got insulation all the way around this container. So that means energy and matter will be trapped inside. This we don't deal with much in chemistry. We look at isolated systems in physics. So we are going to talk about a closed system. So this is the first condition for equilibrium to be able to happen. It has to be a closed system. The second is that it has to be a reversible reaction. So for a reversible reaction, I'm going to use a very simple example. You've seen the vapor one that we've done before. But seeing I found this picture, there is blue copper sulfate and there's white copper sulfate. So in grade 8, what you did is you said you did this experiment and you heated the blue copper sulfate. The water evaporates and the copper sulfate becomes white. So this would be called our forward reaction because we started here. We could have started there as well. Now, that's exactly the point with the reversible reaction. The products of the forward reaction can then be used as the reactants to form products again. So this now, if I just add water, I will go back here. So that is a reversible reaction that has a forward reaction and a reverse reaction. So the products of the forward reaction can become the reactant for the reverse reaction. Okay, very simple reaction, that. Now for that same reaction, let's throw that away. If we look at the same reaction again, so what happens, we now already said, is that the water evaporates from here. Now at 25 degrees, you might not see it. If it's a closed system and you heat it up to 100 degrees, you'll see the color start changing. So now there's water vapor trapped in this area and there are blue crystals. Now the forward reaction, in the beginning, only the forward reaction happens because there's still a lot of water trapped here that could escape. So only the forward reaction happens. And it happens fast. Then in the beginning, the reverse reaction happens slowly, so it's a short arrow. Then there's a point where for every water particle that goes into the vapor state, there's a particle going back into the crystal. And at this point, where the rate of the forward reaction is equal to the rate of the reverse reaction, that is when we reach equilibrium. And we also call it a dynamic equilibrium for that reason. The reaction hasn't stopped. One particle goes there, one particle comes back. It keeps on happening, but you can't see a change anymore. So although the water and the crystals are not equal, that stays constant. So the amount of water that you have there in the test tube now is going to stay constant and the color of the crystals is going to stay constant. So when the concentrations of the products and the reactants stay constant, then you know that you've reached an equilibrium. Now let's just look at a little bit of a better reaction. So if we look at this is called the Haber process. You find it in papers often. You don't need to know the names of the industrial processes, but they often give them to you in papers. So what happens here is we've got N2 and H2 forming NH3. Now the way the question is written this way is always going to be seen as the forward reaction. So the forward reaction, let me just use the colors there. Let's say this is the forward reaction. So if I place this in a container in the beginning, only the forward reaction will happen. So if you look at these two graphs, the concentration of the H2 and the N2 starts high and I've got nothing of the NH3. But I could also start this way and say that this is the reverse reaction. Now, if I look at the reverse reaction, I start with the NH3 and there's none here of the H2 and the N2. So it just depends which way they write to the reaction, because remember, it's reversible. It can happen both ways. Now, the graphs that you need to focus on these are the first ones, is the concentration versus time graphs. Then you're also going to get mole versus time graphs, and often the mole versus time graphs are exactly the same as the concentration ones, because remember, concentration is going to be the mole per unit volume. And if it's the moles per unit volume, it means that if the volume stays constant, the concentration and the moles are directly proportional to each other, and therefore it's the same thing. The graphs will look exactly the same. But when the volume is not constant, then they will not be the same. And that's the only place where you'll see that is for pressure changes. And we'll mention that again when we get there. So now the rate graph. In the beginning, I said only the forward reaction takes place. So let's just make it blue. So only the forward reaction takes place. So the rate of the forward reaction is high because there are a lot of these particles that can undergo effective collisions to form product. So you'll see the rate here in the rate graph. The forward reaction starts with a high rate. In the beginning, there are no product particles, or language. There are no product particles to go back. So after a while, you formed some of these, and now the reaction can happen in reverse. So now my reverse reaction starts to happen from zero rate, faster, faster, faster. Now remember, equilibrium is only reached when the rate of this forward reaction is equal to the rate of the reverse reaction. So therefore, these graphs here must end up on top of each other at the same place, because here the rate must be exactly equal. Not like the concentration graphs where it just has to be constant. So here, whenever it forms parallel lines, at that point, we have equilibrium. Here, when the two lines become equal, is where I have my equilibrium point. So now we're only going to look at the different things that can affect equilibrium, the equilibrium position. Now, what do we mean by equilibrium position? If we're going to favor the forward reaction, we favor the product side. If we're going to favor the reverse reaction, we favor the reactant side. So you're going to look at how these things affect the equilibrium, and we're going to use Le Chatelier's principle to explain these changes in the equilibrium. So what I'm going to do is I'm going to take each of these factors, and remember, it's only these three. Temperature, pressure, and concentration are the only things that can affect equilibrium. There's surface area and a catalyst that affects the general rate of a reaction, and you must keep that in mind still. But these three things will affect the equilibrium position. Now, how are we going? Let's just look at this one here. If I'm going to heat it up more, just to use a simple one first, if I'm going to heat it up more, I am going to form more vapor. So it will favor the reaction which forms more vapor. So that will mean I'm favoring the product side, which means I'm favoring the reverse reaction. But now Le Chatelier gave us a quick and easy way to predict what's going to happen in a system. So he said, when an external stress, now remember it's those three that we spoke about, pressure, temperature, and concentration, is applied to a system in equilibrium, it has to be in equilibrium, the equilibrium point will change to counteract the stress. What we mean by point will change is, again, if we favor the forward reaction, we're favoring the product side. And if we're favoring the reverse reaction, we're favoring the reactant side. Now let's look at temperature change. In temperature change, the delta H value is important. So you immediately have to ask yourself, what is the delta H value? Or sometimes you need to figure it out from the question, but they need to give you information. So delta H for this reaction, this is an exothermic reaction, so delta H is going to be negative. When you get this, immediately go and write for yourself. The forward reaction is exothermic. If the forward reaction is exothermic, it will heat the environment. The reverse reaction is endothermic, because if the forward reaction is exothermic, the reverse reaction, it must be endothermic. So that will cool the environment. And if you've done this, the first 2 marks for an equilibrium question, if for temperature, becomes very easy. Because remember, again, for the first 2 marks, you are not going to look at the actual equation. So let's say the question says it was an increase in temperature. Now, according to Le Chatelier, the reaction will decrease the temperature, and then just think, does endo or exo decrease the temperature? And it is endo. So you're going to say it's going to decrease the temperature by favoring the, and in this case, endo is the reverse reaction, but we're going to not say that yet, by favoring the endothermic reaction. So we didn't even need our reaction yet. Then once we've got that down, then we can say, now you look at the reaction. So you look which one is your endothermic reaction, and we've already written it down. That's why it's easy to do it first. So you're going to say, therefore, the reverse reaction is favored, and then you answer the question. What did they ask? Did we form more of this? Did the color change? Now it's your job to figure it out. All right. So those are the steps. First, say, what is the stress? Second step says, how is Le Chatelier predicting that the reaction will change it? And then the third step is answer the question. Oh, look at the reaction and then answer the question. So the answers that I typed here was for a previous question, but I'm just going to quickly adjust it. So if we look at this one, if we have an increase in temperature here, so the system will decrease the temperature, yes, by favoring the endothermic reaction. But in our reaction here that we just had, the reverse reaction will be favored and more into the more nitrogen and hydrogen forms. There we go. So you've got your steps there nicely in order now. There we go. So first, stress. Second, what will the reaction do? And then you look at the reaction. So please do it like this. Now, I can also do it for a decrease in temperature. So let's see, what if the temperature was decreased? So if I've decreased the temperature, so you're going to say again, what was my stress? My stress was a decrease in the temperature. Then, according to Le Chatelier, the reaction will try to increase the temperature by favoring, now you need to think increase is exo, so by favoring the exothermic reaction. Just say that, don't worry about the reaction. But then we said already forward is exo, reverse is endo. So then you're going to say, therefore, in this reaction, the forward reaction will be favored. And if the forward reaction is favored, more NH3 will form. Now we're going to quickly look at the graphs because I'm going to do each factor with its graph so that you have everything together. Now for the concentration graph, for temperature, concentration, and moles will look the same. Now if you look at this graph here, if the mixture is cooled, we have just said that if the mixture is cooled, the forward reaction is favored. So the forward reaction was favored. That means I'm forming more of this. And you can see that line is going up. So that's what the graph would look like. Then these are used up, so therefore they're used up, so they are decreasing. You should try and do it in the ratios. So if you're forming 2 of these, so if this one goes up by 2 units, the H2 should go down by 3 units, and the N2 should go down by 1 unit. And you can see the diagram did try and kind of get that right. Now, for that's the one graph you're getting. If this was moles, it would look exactly the same because if the concentration increases in the same volume, the moles will also increase in that volume. The next graph that you are getting is a rate graph. Now remember, there are only two rates because there's only one forward and one reverse reaction. So for reaction rate, if we have that little graph there, just throw that one away. For the reaction rate, we have only two reactions, the forward reaction and the reverse reaction. So there's my forward reaction, and then there's my reverse reaction. Now it's already in a happy equilibrium. We're looking at it once it's already reached equilibrium. So it was in equilibrium, and then I went and I increased the temperature. Now remember, it was an exothermic reaction with delta H negative. We said that before. Now if the temperature increases, and here you must be careful. Remember, temperature was one of those things that increases the general rate of a reaction. And that is why we actually don't do these industrial processes at a very low temperature, even if it favors the forward reaction, because the whole rate will slow down too much. So if we look at an increase in the temperature, both reactions, so the forward reaction as well as the reverse reaction, will go up. But now remember, we said for an increase in temperature, we're going to favor the reverse reaction because that's endo. So we're favoring the reverse reaction, meaning that the line for the reverse reaction will go up more. Once they've gone up, now they will form a new equilibrium. So they will then just join nicely again. So until they on top of each other there again. This one is relatively easy, but then people get confused when the temperature actually decreases. So if the temperature decreases, and this, please wake up if you're falling asleep. The temperature decreases, that's my stress, and you went through the Le Chatelier points. Decrease in temperature will favor the exothermic reaction. In our case, that was the forward reaction. But now the temperature has decreased. So the same as the increase, both reaction rates will go down. And this is why low temperatures are not used in the industry, because both reaction rates, forward and reverse, remember this is happening in one container. The total reaction is actually going to happen slower. But now we have favored the forward reaction. So because the forward reaction was favored, it must still end up with a higher rate here. So the forward reaction is not going to go down as much as the reverse reaction because it needs to end up with a higher rate, means more to the top. And then once it has done that, it's going to join up again until they equal on top of each other, where I've now reached a new equilibrium. Make sure you can do the increase and the decrease of the temperature using rate graphs. And that's it for temperature. So the next factor that can influence the equilibrium position is pressure. So I've got many diagrams here, which I don't know if we're going to all use, but the important one that you need to remember is when you have a change in pressure, you actually have a change in volume as well. So here, when the pressure is increasing, I'm increasing the pressure by pushing this plunger down. So this is my volume. So my volume actually decreased. And now you need to remember that concentration is the number of moles over the volume. Now, if my moles stay the same, or when the pressure changes, I'm not changing my mole. So the mole stays the same, but the volume has decreased. And if my volume decreased because it's inversely proportional if moles are constant, my concentration will increase. So I've got a higher concentration now of everything because everything is in a smaller container. The opposite here, if the pressure goes down, I can only get that right by pulling the plunger up, which means my volume is bigger now. If my volume is bigger, my concentration is going to be smaller. Alrighty, let's throw that one away. Now, if we look at a specific reaction and we see how we're going to explain that using Le Chatelier's principle, let's look at this reaction. This is a common one that's often asked. If we have NO2, it is a brown gas. N2O4 is a colorless gas. Now, if you look at the equilibrium here, Now, if I'm going to increase the pressure, now what causes pressure? You need to realize that pressure is caused by particles of gas colliding. So when we're talking about pressure, we only talk about gas particles. So please go and highlight the gas particles if you get a question like this. So these are brown, these are colorless. Now I go and compress this gas. So here I go. I take this gas and I compress it. Now, initially, yes, I'm pushing it down, so I'm pushing these particles closer together so they will get a bit more dense. But now you can see the volume is much smaller. If the volume is smaller, the pressure has gone up. But now the only way I can decrease pressure is by having less particles bounce here against the side. So the reaction will favor less particles forming. So if you look at this, on this side I've got 2 gas particles or 2 moles. On this side I have 1 gas particle or 1 mole of gas particles. So if I favor the forward reaction, 2 moles are changing into 1 mole. So I am decreasing my number of particles. And you can see after a while, the gas will go more colorless. The brown color will start to disappear because I've actually favored the forward reaction. Now again, the steps to answer this. So there we go. If it's an increase in pressure, the increase in pressure was caused by decreasing the volume. No reaction needed yet. According to Le Chatelier, the system will decrease the pressure by favoring the reaction producing less particles, like we just said. That means the forward reaction will be favored, and then you answer the question. You can say more N2O4 will form, or if they ask for the color change, it goes from brown to colorless or less brown. You just answer the question. Remember the 4 steps. Once you've done that, the next thing you need to know would be the graph. So if I look at my N2 NH3 NH3 reaction again, let's just go and steal it from here. Looking at that reaction again. Now let's count the gas particles. On this side, I've got 1 and 3. I've got 4 moles of gas. On the other side, although it's in one container, please remember this is in one container. I've got 2 moles of gas particles. So if I'm favoring the forward reaction, I'm changing 4 moles into 2 moles. So that's less particles, so less pressure. If I'm favoring the reverse reaction, I'm changing 2 moles into 4 moles, and therefore there's going to be more particles, so more pressure. So now how are we going to do these graphs? So let's just look at this one. If the volume was decreased, so the pressure was increased, you're going to still look at the steps. So increase in pressure will favor the reaction, so it's an increase in pressure, will favor the reaction according to Le Chatelier that will decrease the pressure. You're always going to say opposite by forming less moles of particles. Now, if you look at this one, the forward reaction will give you less moles. So then after the second step, you go to your reaction and you say the forward reaction will be favored. Now let's look at the graph here, and you can see this is what the concentration graph would look like. But can you see there's something different? Because I've made the volume smaller, all of these are now in a smaller space, remember? All of these are now in a smaller space. So that means my volume by which I divide becomes much smaller. That is why the lines for all of them must go up first before we go and look at now the forward reaction being favored. Then you can see, okay, forward reaction is favored. So once they all shot up by the same or in the ratio amount, then you're going to show the particles how they're forming more and how they're forming less now for the reactants. So the forward reaction was clearly favored because I'm forming more product. So that's the concentration graph. In this one, you need to be careful because if this was a mole graph and not a concentration graph, so if this wasn't concentration but it was moles, remember if I look back to this reaction again, the number of particles didn't change, just the volume, and that is why the concentration changes. But the moles are still the same. So this steep shoot up thing that happens there for pressure is not going to happen if it was moles. Only the change. So you would see that this bit is still happening. So here, the H2, instead of shooting up first, it will just start going down. And this one, instead of shooting up first, will just start going up. So it's still the same. Forward reaction is still favored. So H2 will still increase and the other two will still decrease, but the shoot up is not going to happen. So you will have your graph looking like that, and then when they go parallel again, I've reached my new equilibrium. So be careful and look, if it's a mole graph, then it will not shoot up or down. But if it is a concentration graph, it will go up or down because of the volume changing. So that's those two, concentration and moles. Now we just need to look at what is the rate graph going to look like. So let's just keep with the scenario the volume was decreased. If the volume was decreased, remember my pressure was increased. But if the volume was decreased, all the concentrations go up. And if you remember from the previous chapter, if concentration goes up, again, both reactions will go up first. And then you look which one will go up more. And we said the forward reaction was favored because it's giving us less particles. So the forward reaction will go up more than the reverse reaction. And then once they're there, then they reach their happy equilibrium again. Okay, so be careful for pressure. It's only the mole graph that's different. Here it works very similarly to the temperature one, but the concentration, you need to remember, will increase both reactions because it's the general concentration that increases. All of these are in the same container. So we make the volume smaller, the concentration of all of them will increase. That's pressure. Now the last one for concentration, the explanation, the 4 points are pretty easy. Now if we look at a concentration change, the easiest one is if they tell you something is added. So if they added something, it will just favor the reaction away from that something. So let's just go through this step. So if I say I've added X, the system will try to decrease the concentration of X by favoring either forward or reverse, but as long as you know that it's away from X, because now I'm trying to get rid of the X that I added. And then you answer the question. So if it was our H2N2 reaction again, you can see I've added, this one shot up. So I added H2. But the reaction is immediately going to try to get rid of it by favoring the reaction away from the H2. So if we look back to our reaction here, the H2 is there. So it's going to favor away from the H2, forming more of this. But when the H2 gets decreased, the N2 goes with it because it's on the same side of the reaction. So let's keep that there. So you can see what's happening with the concentration. The mole graph again will look exactly the same. If I was removing H2, which is going to be very difficult because all these gases are in the same container. So I'm going to show you how the decrease actually works more often. So if I'm taking H2 away, you can see H2 drop steeply. So then the H2 will go up, but the N2 will go up with it. You can see it's quite slightly because the ratio is 3:1. So if this goes up by 3, this only goes up by 1. And then this one will go down by 2. And when it forms a straight line, not a straight line, parallel lines here with each other, then we know the new equilibrium has been reached. Now, this doesn't often happen. We can't just pull one gas out of there because then we're also going to do all kinds of other changes because we're changing the pressure then. So that is a bit hard to do. So what more often will happen is that you have iron. So the common ion effect is very similar to the adding of H2. So if I take that reaction there and I go and add something. So let's say I go and add, what can I add? Let's say I go and add NaF. Now you know this is an ionic substance because it's a metal and a non-metal, and that will split up into Na plus and F minus. Now look for the common ion. There is F minus and there is F minus. So the common ion is F minus. So my stress is actually just the increase in F minus. So then we're going to go through the same motions. The stress was the increase in the concentration of F minus. So according to Le Chatelier, the reaction is going to tend to decrease the concentration of F minus, favoring away from there, which means it's the reverse reaction that will be favored. And I'm going to form more of this stuff on this side. So that one is pretty easy because it's very similar to the one that you had before where we just added H2. But now what you need to look out for is if they say a precipitate forms or an insoluble solid forms. Now I've gone and looked up what forms a precipitate with a fluoride ion, and calcium fluoride is a blue, like you can see there, a blue solid. So when I add calcium, so when calcium fluoride forms, it will be a solid. But now they're not going to tell you you're adding calcium fluoride because that would be a solid that you're adding. They're going to say to you, you're adding something that steals the fluoride out of this reaction. So what they're going to do is they're going to say, we're adding calcium nitrate, for instance. We're adding calcium nitrate. If I'm adding calcium nitrate, remember I'm actually adding Ca2 plus ions and NO3 minus ions. Now look, the question must tell you calcium fluoride is an insoluble solid. When you see that, you need to look for something that you're adding that will form this insoluble solid. One of the ions will be in the substance that you're adding, and one of the ions will be in the solution. So here you can see I'm adding calcium that will steal the F minuses out, and together they will form the precipitate. And this is a solid. If it's a solid, it goes and lies down at the bottom of the test tube and looks at everything else, but it's not part of the reaction anymore. So if you form this insoluble solid, the actual stress is the decrease in the concentration of the F minus ions. And if I've decreased the F minus ions, according to Le Chatelier, the reaction will tend to increase the concentration of the F minus ions. And if you look at that, it will favor towards the F minus ion. So this time my forward reaction will be favored. So please look out if the question says anything about a precipitate or an insoluble solid, it means something, one ion in your solution is going to be stolen out. And the stress is actually the removal of that ion. So if you say, and this should not be increase, if you say that the stress is a decrease in the concentration of any ion, oh man, what did I do now? Fix. If we say it's a decrease in the concentration of the ions, and the only reason why those ions decreased was because of a precipitate forming. So say that. So decrease in the concentration of those ions due to a precipitate forming, and therefore the system will increase those ions by favoring either the reverse or the forward, wherever those ions are, but towards those ions. And then you answer your question. Does the color change or what else happens? And that's the last one, is last thing that can affect the equilibrium. Remember, not the surface area and a catalyst, and we'll look at that just now for a catalyst. But now for the concentration change, if we look at the graphs, it's so the common ion effect will look exactly like this. So your ion will just increase and decrease. But please look, there's no sharp shooting of all the lines. It's just the one line that changes. So if I look at my rate graph, both reactions is not going to be favored. So if it was a common ion that I added, like in this last one, if I favored the forward reaction, that means the rate of the forward reaction is going to increase only. So what you're going to do is you're going to only increase the rate of the forward reaction, which is my blue line. And then we're going to form a new equilibrium immediately. So the red one's not going to shoot up. So if one so it's not a general change in concentration, it's only that one substance that was added, not both substances. So it's just the one concentration that changes. Be careful for that. Now, for a catalyst, remember, if I add a catalyst, it favors the whole reaction. It speeds up the rate of the whole reaction. So it speeds up the rate of the forward reaction as well as the reverse reaction. So what's going to happen for the rate graph? Yes, both of those reactions are faster, but equally faster. So if your reverse reaction goes up by that much, your forward reaction must also go up by that much. And then they both end up there at a higher rate. Okay, remember if it was a pressure graph, let's just go back here. If it was a pressure graph and there are actually the same amount of particles on both sides, then pressure wouldn't affect it, but the volume will still be bigger or smaller. So that means the concentrations will still be higher. So it will look similar to this. So it will have no effect on these. So if you were drawing these, the lines will just keep on going flat because it doesn't affect the number of particles. It just affects how fast they are being formed. So please look out. The catalyst does not affect the equilibrium position. It just speeds up the rate of both reactions. So both lines will go up. Oh, I actually made a space for the catalyst. So, but you know now already. So the forward and the reverse reaction will both go up. So if you add a catalyst, they will both go up and then they will stay at that higher rate. So this is pretty easy. Now for the equilibrium constant, I'm not going to do Kc calculations, but just so that you know, Kc, remember, is the products over the reactants. And the coefficients there, or the numbers there are the coefficients. So for this one, if I was going to write, and you've got this, you need to know this, and sometimes just writing that down counts up to 2 or 3 marks. So please get it right. So, and also, please read your question nicely. If they say the equilibrium constant for the forward reaction, then it's going to be products over reactants. If they say the equilibrium constant for the reverse reaction, then the products become the reactants. So these must swap around and the value will be the inverse. There has been questions on this before, but it just treated the same way. The way the question is written, that is your forward reaction, and they normally ask you for that equilibrium constant. But if the question says specifically the equilibrium constant for the reverse reaction, then you would start by writing these first, and then, or these will be your products, so they will be on top of the line, and these will be your reactants, so they will be at the bottom of the line. Just read your question nicely. So I'm just going to write down the equilibrium constant for this blurry reaction. Kc just means the C means concentration. You also have Ka and Kb in the acid base and Kw for water. So they're all just equilibrium constant. So if I was going to write down the Kc value for this one, I'm going to write down the concentration. Remember, we use square brackets for concentration of the product. So the first product is SO2. So concentration of SO2 square brackets to the power 2 times by the concentration, please times not plus, concentration of O2 because it's a ratio, guys. Concentration of O2 and there's no coefficient because there's just a 1 over the concentration of my reactants, which is SO3 to the power 2. That's my coefficient. Please remember if there's a liquid or there's a solid, they don't change concentration. So the liquid and the solid, you'll just place a 1 instead of a liquid and the solid. So in our Kc values, or in our Kc calculation, I'll only make space for Aq and for gases. The rest I don't have to worry about. Now, Kc calculations, we have loaded just before lockdown a video on how to do Kc calculations. But please remember you must be able to do the Kc calculations, whether you use those tables or you just use plain stoichiometry. Please make sure that you can do the Kc calculations. Now, if this Kc value is very big, then remember the top value is bigger than the small value. So if your Kc value is much bigger than 1, then you know you've formed lots of products. You've got a high yield. If your Kc value is much smaller than 1, then you know I've got more products, so I don't have a high yield of my reactants. So just make sure you know what a high Kc and a low Kc value actually means. A high value means lots of products, a low value means not a lot of products. There we go. Now it's only Kc calculations and you have many videos for that.